Chapter 5 TFT Flat Panel Array Image Acquisition. The first TFT flat panel amorphous silicone and amorphous selenium detectors were introduced in 1995. These were the first devices to move beyond the cassette into detectors that would reside in the table or wall stand. These detectors are no longer permanent fixtures and can be used portably as a wireless device. The materials used for detecting the X-ray signal and the sensors for recognizing the signal are permanently enclosed inside a protective housing. Active matrix flat panel imagers, AMFPIs, consist of a flat panel array with an X-ray absorption material. There are two main types of X-ray absorption materials in use today: photoconductors, which absorb X-rays resulting in electronical charge, or scintillators are phosphorus that produce light when absorbing X-rays. The choice of X-ray absorption material determines whether the detector is direct or indirect conversion. There are two major types of X-ray conversion, which are the indirect and direct. An AMFPI detector measures the response of these materials to X-ray absorption. It is a large area, two-dimensional array of pixels fastened to a thin glass backing. The absorption material is attached to the surface of this array, either electronically, photoconductor, or physically, which is the scintillating phosphor material. The 2D array functions as a very efficient device that measures X-ray absorption rather than counting or measuring the actual X-rays. Direct conversion. X-ray photons are absorbed by the coating material and immediately converted into an electronic signal. The flat panel detector has a radiation conversion material, a photoconductor, typically made of amorphous selenium. So again, test question might consist of the flat panel detector may be typically made of amorphous selenium, or we can see it as A-SE. It's usually between 500 ohms thick for radiography or 200 to 250 for mammography. This material absorbs X-ray and converts them to the electrons, which are stored in the TFT detectors. The TFT is a photosensitive array made up of small, about 100 to 200 ohm pixels. These are also called a detector element, or DEL, in TFT arrays. Each pixel contains a photodiode that absorbs the electrons and generates electrical charges. A field effect transistor, or FET, or silicone TFT, isolates each pixel element. It reacts like a switch to send the electronic signal, or charges, to the image processor. More than 1 million pixels can be read and converted to a composite digital image in less than 1 second. A line of TFT switches, each associated with a storage capacitor, allows electronic charge information to discharge when switches are closed. The information is discharged onto the data columns and is read out with dedicated electronics. Specialized silicone integrated circuits are connected along the edges of the detector matrix. On one side, integrated circuits control the line scanning sequence. On the other, low-noise, high-sensitive amplifiers perform the readout, amplification, and the analog-to-digital conversion. High-speed digital electronics are then used to achieve fast image acquisition and processing. Similar to direct detectors in that the TFT technology is used, indirect conversion is a two-step process. X-ray photons are converted to light, and then the light photons are converted to an electronical signal. A phosphor such as GD2O2S or thallium-doped cesium iodine rapidly absorbs X-rays and produces light. The phosphor layer is known as the scintillation layer. The scintillation layer can be either structured or unstructured. Unstructured layers produce more scattered light than structured layers, thereby decreasing the efficiency of the detector. The light is then converted into electronic charge by a photodetector, such as a hydrogenated amorphous silicone, or photodiode arrays. Indirect conversion. Step 1. X-ray photons striking the dielectric receptor are absorbed by a scintillator or phosphor material in the imaging plate that converts the incident X-ray photon X-ray to light. Step 2. A photosensitive array made up of small, about 100 to 200 ohms, pixels converts the light into electronical charges. Each pixel contains a photodiode that absorbs the light from the scintillator and generates electrical charges. An FET, or silicone TFT, isolates each pixel element and reacts like a switch to send the electrical charges to the imaging processor. As with direct conversion, more than 1 million pixels can be read and converted to a composite digital image in less than 1 second. The GD2O2S detecting material is made from small crystals bound together in an unstructured, powered granules layer along with a polyurethane material. The crystalline layer is filled with air pockets that allow light that was generated in the phosphor to escape. It also allows light to escape laterally before it reaches the surface, reducing the efficiency of the phosphor and lowering spatial resolution. GD2O2S was used primarily for applications that required a rugged detector, such as portable detectors, either wired or wireless. Ruggedness is due to the unstructured phosphor layer. CSI detectors. The most popular type of amorphous silicone detector uses a cesium iodine scintillator. The scintillator is made by growing very thin crystalline needles perpendicular to the detector surface that work as light directing tubes, much like fiber optics. And when you're looking at the image to your right, you can kind of see how that would remind you of fiber optics. Because of how the cesium iodine crystals are grown, they are considered a structured scintillator. Needles can be evaporated onto the surface of the layer or can be grown with a seed layer. This allows greater detection of X-rays, so higher DQE than GD2O2S scintillator, and because there is almost no light spread, the spatial resolution is higher. CSI detectors. These needles absorb the X-ray photons and convert their energy into light, channeling it into an amorphous silicone photodiode array. In the past, CSI detectors could not be practically used in a portable type detector. The crystalline structure was too delicate to be used outside of a protected environment of a fixed detector array. Because of the advances in materials and crystalline formation of the array, both CSI and GD2O2S are being used in portable detectors. Flat panel array design and performance. The way an ASI H-array functions is very complex, but the design is fairly simple. Each pixel contains a sensing component and a switching component. There are two types of switching components: two-contact switching diode and a three-contact TFT. The sensing component depends on the type of absorbing material and the vendor's choice of structure. A phosphor scintillator requires a photodiode or phototransitor to detect the light. If a photoconductor, ASE, is selected, the sensing element is a capacitor that measures charge. This is also known as storage capacitor. For the flat panel detectors to operate, there are about 2.5 kilometers or 1.6 miles of electrical bias, a predetermined amount of voltage or current in an electrical circuit, control and signal output lines laid out on the array surfaces so that each pixel is monitored and refreshed during the control and reading process. Each row of pixels is connected to the same horizontal control line, and each column is connected to the same vertical data line. The readout electronics are attached to the edges of the array, and the entire array and its components are enclosed in a protective housing. Flat panel array design and performance. When the exposure is made, the sensing and storage component within the pixel contains the image information. The information is read out line by changing the control line voltage. Each pixel is connected to its corresponding data line at the bottom of the column. The process of returning to this state varies per vendor. After release of its signal, the readout process continues to row 2. After the signal has been released, the energy is then transferred to the electronics that are attached to the edges of the array. Figure 5-7a illustrates the detector in the initialized state, preparing and waiting for exposure. In image B, the detector has been exposed and it's waiting reading of the array. C demonstrates the readout or release of signal of row 1. Notice that the voltage is applied across the control or switch line corresponding to row 1. In image D, row 1 has returned to an initialized state. There are two ways to measure detector performance: numerical measurement of spatial resolution in DQE, and observation of low contrast objects in a contrast detail phantom. Current performance measurement of signal to noise ratio in DQE support that flat panel ASI. H detectors perform better than other digital imaging systems. There is a possibility of any imaging system of losing or misrepresenting image information because of defects in the operation components of the device. Although not very common, artifacts can be caused by malfunctions in the detector: dead pixels, incorrect gain calibration, image lag, and incorrect offset correction. Because manufacture of these pixels is so complex, it is inevitable that the array structure will sustain some damage. Dust, scratches, static discharge, chemical corrosion, and interactions between materials can occur, resulting in some defective pixels. Dead pixels. Some pixels may be malfunctioning or dead, not functioning at all. As the detector ages, the number of dead pixels increases. These may not be detected if they are located on the edges of the panel. Manufacturers make efforts to maintain a standard of less than approximately 0.1 to 0.2 defective pixels and build software programs into their systems to identify and isolate dead pixels. So need to know information that they want less than 0.1 to 0.2% for defective or dead pixels. The software uses an interpolation method to fill in the dead pixels with information using the surrounding pixels as a guide. Incorrect gain calibration. Gain calibration is used to correct flaws in the detector. If an area of the detector has a large amount of dead pixels, or if there is an area of the detector that has poor connections between the conversion layer and the ASI TFT array, a noticeable artifact can be seen on the screen. To remove the potential of having that artifact interfere with diagnosis, a process known as gain calibration or flat fielding occurs. This process will remove these densities of the image by creating a mask of those defects. When a subsequent image is taken, the software will use the mask to remove the unwanted densities and leave only the diagnostic information. Gain calibration should be performed under the same or similar circumstances in which clinical images will be taken. The calibration should be done according to the equipment manufacturer's guidelines. Looking at figure 5-8, notice the AEC cells that appear as slightly positive squares in the image. The gain calibration was performed with the detector outside of the bucky, and then a subsequent image taken with the detector in the bucky. This could happen if anything is left on the detector during a gain calibration. These faint marks could lead to misdiagnosis. Some flat panel systems have the ability to take images faster than a detector can accommodate. If an image is taken before the detector releases all of its signal from the previous image, a faint image of the previous exposure may be visible. This is known as image lag. Image lag is almost a double exposure of sorts. When the detector is unable to eliminate all of the signal from the previous image, lag can occur. Rapid succession of images is only one reason for image lag. Another reason image lag might occur is overexposure of an area with little beam attenuation, such as technologist lead marker location. In figure 5-9, you will see a faint R in the proximal thoracic spinous process. The R is left over from the previous image. To reduce the possibility of image lag, increase the amount of time between exposures, giving the detector sufficient time to release all of the residual image. Consult the equipment operator's manual for suggested image intervals. Reduce the amount of unattenuated beam by collimating as closely as allowable. Set appropriate technical factors for each body part being examined. If multiple exposures are being done, acquire the image requiring the highest technical factors last. Image lag can also be corrected with the detector software using the dark noise or offset correction. Offset correction determines the amount of signal inherent in the detector. If an offset correction is performed before residual signal leaves the pixels, the information will be stored as an inherent and could cause a negative image on the residual signal. Always follow the equipment manufacturer's guidelines when performing any detector calibrations. For example, in Figure 5-10, an offset correction was performed after an exam was done with a right marker in the area of unattenuated radiation. Residual signal remained in that area, and a subsequent offset correction was performed. The R is now viewed inversely because the signal created a mask during the offset correction. In Figure 5-10, you will notice the signal is still very strong, and the image was taken 10 minutes after the initial exposure. Emerging technology. In conventional projection imaging in the past, an imaging technique called tomography was used. Tomograms were acquired by attaching a fulcrum to the Bucky and tube head. The Bucky and tube head would move in concert with one another, and the tube would arc across the patient. The fulcrum point would determine the area in the body imaged. This same concept is now being used in digital imaging and is called tomosynthesis. Tomosynthesis was not previously possible because earlier digital detectors were not able to acquire images rapidly in succession. With advances in selenium detector and amorphous silicone TFT arrays, the detector is now able to acquire images at the rate of 30 frames per second. After the acquisition of the entire set of frames required for the body part being imaged, the frames are sent to a post-processing workstation for reconstruction. The images are then sent to a viewing station as a stack of images, similar to a stack of computed tomography images. The image can be viewed as single slices or in a SIN mode like CT. This is just showing you an example. Currently, most tomosynthesis is being done in breast imaging, primarily for patients with very dense breast tissue. There have been several studies done looking at the benefit of this type of imaging on the extremities and chest. As technology becomes more readily available, more applications will be put into use in the imaging modality. Chapter 6. CCD COMS Image Capture. Charge-coupled devices. The oldest indirect conversion digital radiography system used to acquire a digital image is charge-coupled devices. Hint, hint. So X-ray photons interact with a scintillation material, and the signal is transmitted by lenses or fiber optics to the CCD. During the transmission process, the lenses reduce the size of the projected visible light image and transfer the image to one or more small capacitors that convert the light into an electronic signal or charge. This charge is stored in a sequential pattern and released line by line and sent to the ADC. Structure and function. A CCD is made up of a photosensitive receptor and electronics embedded in a substrate material in a silicone chip. Incident light from a scintillator strikes the detector and electron. Hole pairs are produced in the silicone. The amount of electron hole pairs is related to the amount of light absorbed. The electrons are held by electrostatic forces in the array until the charge is read out to form the image. The chip is made up of a polysilicon layer, a silicon dioxide layer, and a silicone substrate. The polysilicon layer is coated with a photosensitive material and contains the electronic gates. The silicon dioxide layer is an insulator, and the silicone substrate contains the charge storage area. Hint, you may need to know the difference between these three items. The detector element, or DEL, contains three electrodes that hold the electrons in an electrical potential well. The DELs are performed by voltage gates that, at readout, are open and closed like gates to allow the flow of electrons. To collect the charge of the silicone chips, the voltage sign is changed on the electrodes within each DEL, moving the electrons by rows down the columns until the readout row is reached. This commonly known as the bucket brigade scheme. When the readout row is reached, data is sent sequentially to the sense amplifier and are digitized. The readout process requires that the movement of the electrons is timed. Multiple voltage changes occur very quickly. Overfill of the DELs will cause a blooming effect. Excess electronics spill out of the DEL into an adjacent DEL. Overflow drains are built into an array to reduce or prevent this effect. Image-related characteristics. It is not practical to manufacture a CCD chip larger than 5 centimeters by 5 centimeters. Most range from 2 to 4. The image must be matched to the size of the CCD. CCD technology uses lenses or fiber optics so that the image matches the receptor size. Reducing the image size involves several components that contribute to the quality of the image: scintillator, light collection component, and noise. The scintillator and the way it is constructed will determine how many of the incident X-ray photons are absorbed, how much light is produced, and the wavelength or color of the light. Scintillator. The two main types of phosphors are structured and unstructured. So CSI is considered structured because of its needle-like crystals. GD202 is considered unstructured because of its powder-like grains. So CSI needles focus light into a very narrow area, reduces light spread, and allowing the use of thicker scintillators, minimizing the loss of spatial resolution. Turbid phosphors produce more light spread, resulting in decreased efficiency of the detector. Image-related characteristics. The optics in a CCD are critical contributors to the quality of the digital image. Lenses or fiber optics focus light onto the CCD chip. The efficiency of the transportation of light to the chip is important because of the noise created. The more light that is sent to the chip without creation of noise, the more efficient the system is. The design of the optics is also crucial in imaging performance. Issues arise with geometric distortion, such as light scattering or lenses of optics flaws. The amount of electrons produced relative to the incident light from the scintillator is the quantum efficiency of the CCD. Quantum efficiency represents the absolute efficiency of the light collection and signal created in this chip. Quantum efficiency affects detective quantum efficiency. DQE is the ratio of output signal to noise ratio. Quantum efficiency. The CCD is built to be as efficient as possible. The polysilicon layer must be transparent enough so that light passes through it to the deeper substrate storage area, but not so deep that it cannot be captured into the potential well. The spectrum sensitivity must match the spectral output of the phosphor. The less sensitive the CCD to the light spectrum of the scintillator, the less efficient the CCD. Several types of noise are associated with CCD technology. The most common three are statistical noise, dark or current noise, and amplification noise. So noise. Statistical noise is created by lack of light photons from the scintillator. This is known as quantum model. If there are not enough X-ray photons striking the scintillator, if too few light photons are produced by the scintillator, then too few electrons will be generated and the output signal will be noisy. Dark or current noise occurs when the CCD chip operates without radiation stimulation. When the temperature rises and electrons are moved into the bulk silicon layer or depletion area, at readout unnecessary information is added to the image. Some manufacturers add thermoelectric cooling devices that drop the temperature as much as 40 degrees Fahrenheit, lower than the room temperature. Dark noise can be as much as 10,000 electrons per pixel per second. A 40-degree drop can reduce dark noise by a factor of 100. Amplification noise is common in digital systems, and these are no CCD without it. The response of each CCD chip will vary across the array. Some pixels may not work at all. Software is used to correct the statistical variation caused by inoperable pixels. The more bad pixels, the worse the detector efficiency. The cheaper the CCD, the more defects. CCD applications are used in several applications in radiography, including digital, fluoroscopy, stereostatic breast biopsy, digital mammography, and general radiography. Digital fluoroscopy. The CCD is a great replacement for the television pickup tube and image intensifier. The CCD size, 2 to 5 centimeters, is closely matched with the output phosphor of an image intensifier, 1 inch. The CCD readout is linear and has a greater dynamic range than a TV tube. Oversaturation is almost zero. Blooming is greatly reduced, shortening the recovery time from one image to another. CCDs are more compact than TV tubes. CCDs are not susceptible to electronic scanning errors. Stereotastic breast biopsy. A single CCD detector can be used because the typical field size is 50 millimeters by 50. Most current systems use a 2.5 centimeter by 2.5 chip that results in some demagnification. Demagnification is a process of reducing the phosphor output image to the size of the active area of the CCD chip. Hint, might need to know what demagnification is. Lenses, optics, and mirrors are used in the process. Noise is not as much of a factor because of the low dose. Newer digital mammography systems are replacing CCD with flat panel technology. General radiography. CCDs may be tiled in a 10 by 12 array to a single CCD. CSI is a common scintillator material. Again, hint, hint, might need to know that a CSI is a common scintillator material. Whole body scanners are used in trauma and forensic pathology applications. 12 CCD cameras are coupled to a gadolinium sulfur dioxide scintillator that tapered with fiber optics. The tube and receptor array are housed in a C-arm type mount. The fan beam, slot scanning device, moves down the length of the table or stretcher. The scan can be any length up to 180 centimeters. Advantages and disadvantages. CCDs are simple and modular. They're easy to repair, replace, and upgrade. CCDs are relatively cheaper than TFTs, based flat panel systems, and demagnification issues reduced DQE. Complementary metal oxide silicone. CMOS systems were developed by NASA. Hint, important information is that it was developed by NASA. It uses a scintillator that, when struck with an X-ray photon, converts the X-rays into light photons and stores them in capacitors. Each pixel has its own amplifier, which is switched on and off by circuitry within the pixel, converting the light photons into electrical charges. Voltage from the amplifier is converted by the ACD, also located within the pixel. The system is highly efficient and takes up less space than CCDs. Voltage from the amplifier is converted by the ADC, highly efficient and takes up less space than CCDs. CMOS is a semiconductor, a solid chemical element or compound that conducts electricity under some conditions but not others. A good medium for the control of electrical current, and its ability to conduct varies on the amount of current or voltage it receives or on the intensity of radiation X-ray. Impurities, also known as dopants, are added to the semiconductor to make them highly conductive. Hint, impurities, dopants. Semiconductor materials do not conduct electricity well on their own. Typical semiconductor materials are antimony, arsenic, boron, carbon, germanium, selenium, silicon, sulfur, and tellurium. Silicon is the most popular, and it is the base material of most integrated circuits. Again, silicon is the most important or popular. So common DuPonts added to silicon are gallium arsenide, indium, antimony, and oxides of most metals. When duped, the semiconductor becomes a full-scale conductor with extra electrons becoming negative charge, N-type transistor, or positive charge carriers, P-type transistors. Most CMOS semiconductors have both N and P-type transistors, so they can form a gate that can be controlled electronically. CMOS transistors use little to no power when not needed. Rapid current direction changes will cause the transistor to become hot, and this will cause the microprocessor to slow down. CMOS image sensors convert light to electrons that are stored in capacitors located within the pixel. During readout, the charge is sent across the chip and read at one corner of the array. At each pixel, several transistors amplify the charge and send it through the wires of the array corner. An ADC turns each pixel value into a digital value. Comparison of CCD and CMOS technology. CMOS sensors are more susceptible to noise. Light sensitivity of a CMOS chip is lower than a CCD. In a CMOS, the pixel is surrounded with transistors, and many of the light photons hit these rather than the photodiode. CMOS uses very little power. CCDs may use as much as 100 times more power. CMOS is less expensive to manufacture. They tend to have lower quality, lower resolution, and lower sensitivity, but the technology is improving. Pixel fill factor is greater with CCDs than CMOS. Important to know the differences between CCD and CMOS. Despite their differences, these technologies both provide excellent image capture capabilities and both depend on the type of application. Each has strengths unique to these applications, and neither is superior to the other. Medical imaging will continue to see growth and new applications for both CCD and CMOS detectors. CMOS detectors or designers are working to increase quality, while CCD designers are lowering power requirements and pixel sizes.